Hello and welcome to another review lecture for operating systems class. Today we're going to be focusing on chapters 1 and chapters 2. Chapter 1 being the quick overview of the entire course, and chapter 2 diving into some key ways in which we interface with our operating system and the operating system interfaces with the hardware. So the main point of chapter 1 was to try and give you an understanding of an operating system's responsibilities. Our OS is meant to provide services to the user, right? So the idea behind an operating system is that we need some kind of base functionality to load on every computer on which we can build. And when I say we can build, I mean you can add more programs on top of to do meaningful things. Right? We need some user interface that we can interact with that's consistently there so that we can load new programs and run them. We need a way in which we can interact with our OS. That's going to be our system call API. One of the main jobs our OS will do, and we'll see it's kind of the main focus of our entire course up until the reading week, is program execution. We need to be able to execute many programs at once concurrently in order to get the most out of our system. We're going to need some kind of support for I/O operations. So how do we get inputs from our user or outside world and then proceed to output things back to that world? A computer without I/O doesn't really interact with much, right? We need permanent storage on our system, ways to interact with it and manage files. We're going to need some mechanisms like IPC to support program execution. And then finally, we should have some kind of protection, security, and error detection. So these are the things that you actively see and engage with, but behind the scenes, your operating system has more responsibilities, primarily being managing shared resources. So the operating system came around with the goal of wanting to get the most out of our expensive computer systems, right? A computer is very costly, and you want to get as much meaningful work out of it as possible. And obviously, in current years, computer prices are coming down and down, but that doesn't mean that we want them sitting idle doing nothing, right? You want to get the most out of your hardware. When we talk about resource allocation, we're going to be talking about CPU cycles, space in main memory, file storage, permanent storage, any I/O device interaction. Right? Our operating system manages all of this and assigns it to the running programs. So that's, in general, what we have our operating system doing, kind of taken at a very high level. I feel like it's important to note that these videos don't replace going to class, reading the textbook, or watching the full lectures. They're meant to just jog your memory on the types of things we talked about in the chapters and what I think is most important to have learned during that. All right, so this is what is inside the box of your computer. So if you open up the box, you'll find all of these things. The reason why I felt it was pertinent to point you to these things is because this is what our operating system manages, right? These are the hardware resources that our OS needs to work with. When we talk about an OS's responsibility, right, a lot of it is deciding which program gets to occupy our CPU, who gets to go where in our main memory, our RAM. We talk about who gets to talk to our peripherals, right, like our Wi-Fi card or maybe a disk drive. We manage all of our storage. So that could be an SSD or an HDD or any other kind of permanent storage device, right, etc. So when we're looking at our model of our computer, we're going to have some kind of CPU. This is where our processing occurs. It's connected to everything over a system bus. The system bus will talk with main memory. It's important to note that main memory is volatile. This is our RAM. And what that means is if we power off our computer, it doesn't actually save anything. This is just our working memory. It sits close to our CPU. So whenever we're running a program, we're going to store that program in here. We'll be reading the instructions that our CPU needs to execute from main memory and saving all of our data there too. However, if you want to save something permanently, you should do it on one of your disks, one of the SSD or HDDs shown in this picture, right? And that'll be done using some kind of file system managed by your OS. All of this stuff up here in this top corner of this picture, these are all considered I/O devices, right? Your core system is going to be the CPU and main memory. Everything else is going to live outside of that, and will interact with it through the operating system. So after reviewing and attending the lectures for the first two chapters, I expected you to have built up a mental model of our system, right? So we learned about three different kinds of programs that run on our computer. We said we had these things called application programs, system programs, and the OS kernel. So the application programs, these are the types of things that users might download and install on their system. They're entirely in the user space. They're high-level programs that offer some kind of service that the users want. So, Microsoft Office Suite, your web browser, all these things, any applications you might download and install on your computer. Then we said kind of one level lower than that, but still in the user program space, we had system programs. So these will be the programs that ship with your computer, but aren't part of the operating system kernel. So things like your compiler, your user interface, your shells, maybe a simple text editor, these are things you expect with your operating system to come out of the box, and they're important. Without them, you wouldn't be able to use your computer system, but they're not so important that they run inside your kernel. We had this divide, this hard divide between user space programs and kernels programs, right? We said programs that are in our kernel are special. They run in a higher privileged environment. They can do more things. This is the core of our operating system. All of these things are key core OS functionalities that we need in order to provide the features that our operating system said it provides. Right? Something, maybe a key way to tell if something's in your kernel, if something's a system program, you can replace these system programs with application programs, right? You can download new UIs, you can download new text editors, you can download and install compilers, you can heavily modify your UI. These are typically things that run in user space, and the users can work with them, replace them, all those things. It's much more difficult to modify these things in the kernel, right? You need administrator access on your system, and probably the OS needs some kind of mechanism in which you can modify these things. So the important thing to note about this slide is, and this is just one of a few of the slides that have this picture, right, is the interfaces. So chapter 2 was mainly, and I guess parts of chapter 1, the main takeaways I wanted you to gather were these interfaces between user space programs and the kernel, and then also between the kernel and the lower level hardware devices, right? So we said the users interface with our operating system kernel through these things we call system calls, and then the operating system kernel manages all of the hardware and eventually will actually control those devices through things called device drivers. And what this modularity enables us to do is we can create a common API for system calls such that system and application programs can run on different versions or different operating systems altogether, provided they have the same system call interface. And likewise, below, we can swap out components inside our computer without remaking our full operating system. Instead, we just swap out the individual device driver, right? So maybe let's say we wanted to install a new networking card on our system. Maybe the networking card had a different manufacturer. We don't have to redo our entire OS. We don't have to write different code for our system. We just download the device driver from the manufacturer of our new networking card, slot it into the appropriate position in our OS, and everything else can stay the same. So that's one of the key takeaways from this first chapter. So the primary one that we'll be talking about there was the system call, right? We said that this was the way in which user mode or user level processes can interact with the operating system. So one of the key things the OS does is it provides these services to the user. And it can do that through an API. So we learned about POSIX and what a system call API might look like. So there's different versions of this API, and different systems will use different ones. Now, we learned about these two distinct modes, right? And we said that user versus kernel mode was distinguished by this special bit called a mode bit, right? And using that mode bit, we could have this layer of security which prevented user mode processes from executing special privileged instructions. So user processes were not allowed to do certain things that we determined were of such high importance we only want to let the OS do them. And this gave us a layer of security, right? But it also meant that user processes couldn't do a lot of things, so we need these system calls as a way for the user to request those maybe privileged operations be done by the OS. Now, an important note here about system calls is that they're more than a normal function call, right? There's going to be extra stuff we have to do, meaning they have more overhead in the form of context switching, because we have to change from user mode to kernel mode and possibly change to executing something in the context of our kernel instead of in the context of our user process. So how that typically would look, right, is we have these mode bits, and we define user mode as being mode bit 1 and kernel mode being mode bit 0 in this class, but these are arbitrary, right? We have one mode that says we're in user mode and one mode that says we're in kernel mode. And special high priority functions like modifying operating systems data structures are only going to be done in kernel mode. If a user tries to change these things, that would constitute an error and we would stop the user's program from running, right? This would mean that the user was either making a mistake or maybe worse, being malicious, and we don't want that. So when a user process is executing and it decides it wants something from the kernel, right? And maybe that's, I want more memory because I'm out of memory, right? We say, OS kernel, please give me more memory. That might look like a system call. So we'll make a system call to the kernel. We'll say, kernel, we want this thing. And what happens is a special thing called a trap or a software interrupt occurs. And I'll dive into that a little bit more on future slides, but know that when we get a trap, we get one of these more complex context switches to switch into kernel mode. And so we'll switch the mode bit and we'll give control to the OS kernel. The OS kernel can then decide if that's a reasonable system call to be made by this process. So it'll check the appropriate security measures and execute the system call if it's all above board. When it's done, right, it'll return the mode bit as it was and toggle back to user mode before returning to the context where the system call was made. And then the user process gets to keep executing. Right, and this way we can keep certain operations protected around kernel mode bit being 0 or being in kernel mode. All right, so now a little bit more detail on how we go about making these special types of calls and how we transfer from user mode to kernel mode. So something you might be aware of from previous classes, or maybe not, are things called interrupts, right? Interrupts are typically originally taught in the context of hardware interrupts, but in this class we'll be talking about software interrupts as well. So in the traditional scope of hardware interrupts, we're going to have a special line that goes into our CPU. We call this line the IRQ line or interrupt request line. So there's going to be some wire that goes to a pin on our CPU that tells it when an interrupt has occurred. It just says, hey CPU, there is an interrupt. Typically this IRQ line will come from some kind of interrupt controller, and the interrupt controller will be like a multiplexer for many interrupts. It's a bit more detailed than we need to get into for this class, so I'll leave that as kind of an exercise for the reader. I went over it in lecture in my aside on hardware interrupts. But what you needed to know for our class, this is specifically geared towards Comp 3000, is kind of the general process that happens when we experience an interrupt, so we can apply it to the software interrupts that we see in this class for mode switching. So just briefly here, I wanted to show you the von Neumann architecture as kind of a reminder about the things that go on inside our CPU. So this is another model of a computer system where this box here, this smaller box, is the CPU, the central processing unit, which is split up into a few different things. And then we have the memory unit. The memory unit's going to be what manages our main memory. So we can see the CPU and main memory are heavily intertwined. We've got them inside the same gray box, whereas everything else on our computer exists as input devices or output devices. So now in our CPU, we've got the control unit, the ALU, and some registers. So we won't go into too much detail about that. That's more of a computer organization course or architecture course where we're more focused on just how do these hardware interrupts work so that we can use that concept to change from user mode to kernel mode. So first, I wanted to point out that in our registers, we're going to have flag registers. These registers just say certain configuration information. One flag register it's going to contain the mode bit. So one of those flags is the mode, and we can tell by whether or not that mode bit is 1 or 0, whether or not we're in user mode or kernel mode. This is important because the protection we get from this mode bit comes from actual hardware. So our CPU, when executing an instruction that is either appropriate or inappropriate for kernel mode, can tell whether or not it should be allowed and then raise an appropriate error. If a privileged instruction gets ran, well, the mode bit isn't in the correct position. And then other registers are going to be things like our program counter. The program counter just says which instruction is the next to be executed in main memory, so it points to the correct location in memory to load the next instruction. And we've got a number of accumulator registers that are just working registers for changing things, among many kind of other things. So the other thing I wanted you to kind of learn out of this image of the process with this register set and the explanation on what our registers are is that a given running executing program is going to be captured, its state will be captured by the set of registers. So if we know the correct value for all of the registers, and main memory is all the same as it should be, by saving and loading these register states, we can save and load a program that was executing. So if we take a snapshot of all the registers, right, and save it for later, when we restore that snapshot, we can resume the execution of the process. So that was something I hoped you picked up on when we talked about registers. Anyway, what happens here when we get an interrupt, right? We see the IRQ line goes high. The CPU's control unit, which will be responsible for the fetch execute cycle, will at some point in that cycle check for the IRQ line. When it sees the IRQ line has gone high, it will execute the appropriate interrupt handling sequence. All right, and for hardware interrupts, what that sequence looks like is shown right here. It seems intimidating, but the set of instructions is fairly intuitive, I think. So we see that our CPU is going to finish its current instruction in its fetch execute cycle. When it's done its instruction, it's going to check an interrupt flag. This interrupt flag is directly connected to that IRQ pin we saw coming in. So if a process has interrupted, that flag will be raised to high. So that means it's set. There is an interrupt. Now, in the context of a hardware interrupt, this is what we do, right? So we'll automatically save our CPU state. This is going to be an accelerated hardware circuit. So that in hardware, we're going to do this automatically. We have to do this often, so it makes sense to do it in a way that's as fast as possible. Then we're going to go to the interrupt controller. That's the device that keeps all of our interrupts managed, and we'll ask it for something we call a vector number. So the interrupt controller will have, say, however many interrupts you have on your system, it'll have inputs for all of them, and one output. And then based on each input, it'll know which number it is. They'll be assigned a number we call the vector number. So each device will be given a unique ID, a unique vector number that's associated to it. And the appropriate handling function will be bound into a table, the vector table, right? And the vector number is actually just an index into that table. So we can, hypothetically say our keyboard is interrupt 0 and maybe our mouse is interrupt 1. This is obviously a simplified example, right? But when we get an input from our mouse, we'll get an interrupt with vector 1. And when we get an input from our keyboard, we'll get an interrupt with vector 0. And then in our vector table, we'll bound the appropriate functions. So if 0 is our keyboard, the key capture or keyboard update handler function will have its actual address input in the table at entry 0. So each of these entries will have the address of the ISR. ISR is just the interrupt service routine or interrupt handler, right? So we can use the vector to look up in this vector table to find the appropriate function. We can then jump to the ISR, so that's the same as just calling the function, right? We want to set our program counter to equal whatever the starting address of the ISR is so that we can execute it. And that'll handle capturing the input or whatever the interrupt was for. So, for our keyboard, it might be, read from the keyboard's buffer what keystroke was input, and then clear the interrupt. After we're done handling the interrupt, it's going to return. It's going to return to the interrupt handler in the OS, and the interrupt handler is going to decide if it needs to make a scheduling decision. So during the course of the interrupt, maybe something changes within the context of our scheduling algorithm. If that's the case, right, then we might want to schedule a different process than was running before. So typically there'll be some kind of flag that can be set during the ISR, and if the ISR influences a scheduling decision, it'll set that flag so that we invoke the scheduler only when needed. So presumably we get through our scheduling, which decides which process we should restore, then we can go to the dispatcher or whatever to restore the appropriate context, appropriate user space process. So now this is how the steps are done for hardware, and this existed first, and then we introduced the idea of software interrupts. So we kind of took advantage of the fact that we had hardware acceleration for all of these things, and we bound in this extra idea called software interrupts. Software interrupts, they let you reuse these steps, only the interrupt doesn't come from an actual hardware device changing a voltage on a line. Instead, it comes from invoking an instruction. So for specific software interrupts that we call traps, they invoke a special instruction, usually called INT or something along those lines, with an integer. And the integer is actually the vector number. So it tells you which specific handler to load. And then we'll use this for our system calls. So when we make a specific system call, they'll invoke a software interrupt, which will perform all of these steps with an added step, which is they set the mode bit. So after saving the CPU state, right, they're going to set the mode bit here in step 4. So maybe they don't need to ask the interrupt controller for the vector number, because when they interrupt with a number, that number is the vector. But they do set the mode bit. And by setting the mode bit, what that does is it lets us execute the system call in higher priority. All right, so we came up with this sort of a summary of all the different kinds of events that can occur on our system. And we classified them as 2 sort of categories, and these are still sort of somewhat generic, but we have this idea of external hardware generated interrupts. These are going to be the things that actually raise our interrupt service, the IRQ line there, asynchronously at any time that we don't know about, right? So they don't have to happen with our CPU clock. These just happen from external devices. Then we have this set of synchronous events that can occur that use the same hardware and systems. So we have these exceptions, which might rise as any of these 3 things. And the key difference between these external interrupts and then these exceptions are that these exceptions can be generated, they're always generated synchronously, so with our clock, because of executing an instruction. So maybe the easiest kind of exceptions that can occur are aborts or faults. These are things that happen that aren't allowed. So if you execute an illegal instruction, your CPU is going to generate this kind of exception. It's going to create a software interrupt and call the appropriate exception handler, right? And you can bind in your own exception handlers for these, or you can get generic default ones, but it'll be for handling things like illegal instructions. And in those cases, usually the process just terminates gracefully. The next type will be faults. Faults are things that happen that aren't bad, but that maybe we don't want. right? So usually they're recoverable things that maybe need some management, and then you can retry. So the fault we'll talk about most in our class are page faults. So these occur when you try and access some main memory value that's not currently loaded in main memory. So you want to access some memory from your process that's currently not in main memory. And we'll maybe make some more sense of that once we talk about virtual memory and memory management. But just know these are things we can handle. These are things that we expect to occur, and they just need some help. So we'll manage whatever, we'll fix whatever went wrong, we'll fix the page fault, and then we'll retry the instruction. And then finally, the ones we're talking about in this lecture, this sort of these chapters, right? This is the trap. So these are going to be things we did intentionally on purpose, right? And these are what we use for system calls. So this is when we invoke that special interrupt function with a specific integer value for our vector number. So if we want to execute the read or write system, let's say read system call, it'll be assigned a specific number on our system, and we can invoke that interrupt. Well, we'll call the system call API, right? And the system call API, what it does is it invokes that interrupt instruction with the correct vector number, so that all of the previous slide steps occur, and we can toggle the mode bit automatically. And we know that after toggling the mode bit, we're going to land in some, kernel mode, the kernel mode being, interrupt handler, which calls the appropriate function. So we know that the receiving end of this trap is going to be not only going to be the specific, system call we made, but it's going to be executing in kernel mode safely. So we don't have to worry about a user executing code in that space, because we're calling a specific function from a table of valid functions that are allowed to run in kernel mode. Which brings us to the system call OS relationship, right? So we can see here we've got some user application, right? The user application is going to call some system call through an API, and now maybe that can be the C standard library, or maybe it could be directly with like an API like POSIX, and they'll call this, say the open system call, which opens a specific file. And that open system call is going to rely on, and we'll learn more about this in the file system chapter, but it's going to rely on modifying some operating system structures so that the given program can access a file. And that obviously needs elevated privileges, so we're going to interact with our system call interface. And that system call interface will involve one of these software interrupts, a trap, which will flip us into kernel mode and look up the appropriate system call in the system call table or vector table, right? So each system call is going to be given an integer index into this table. So we'll find, open is value I. We'll do a lookup to I, and stored here is the address of the open function, the actual system call itself. So our system call interface or interrupt handler will look up in this table and call the appropriate function. So that points really here to the start, to open, and this is the implementation of the open system call. And we can execute this, and when we return, we can return to the system call interface, which then decides if, do we need to make a scheduling decision, and if not, we'll restore the application that called us. Okay, so that was kind of a quick rundown of system calls. Understanding system calls is very important. The other interesting thing that we talked about in this chapter was the different operating systems architectures. So we learned about these 5 different architectures. I'm not going to recover all those slides. I posted the lectures on Brightspace, so if you want to hear the full definition of each one, watch the lecture again. But it is important for you to know the trade-offs between these architectures, right? So remembering maybe what is the difference between something like a microkernel and a monolithic, or microkernels and modular, and then how they work together in hybrid systems so that we can create perhaps better operating systems for specific use cases. And the reason why I say this is interesting is because in these architecture decisions are encoded a lot of trade-offs, and those trade-offs will decide, whether or not a specific operating system works well in an environment or not in another.